All right, thank you. It truly is an honor to be a part of this program. We appreciate the Swine Group and Dr. Day letting the Feed Science Group report some of our data, and it's really been exciting to see how much this room fills up every year. There's not many seats available this year. So as we've heard this morning, there's been some talk about pigs reading protocols or not reading protocols, and in the Feed Science Group, we kind of have our own saying that everybody has a protocol until the pellet mill plugs. And so I want to start off by thanking my group of the grad students, Dr. Stark, and then Chance Feeler and Haley Wecker at the feed mill for making all this happen, because as a nutritionist planning feed science research projects, I tend to plug the pellet mill a lot. So without their help, we wouldn't have a lot of this data today, and once again, the royal we is really the work that they've put in. So what we're going to discuss, quick update on some QA procedures, things you can do to help the accuracy and precision of your results with your QA program. And then we'll kind of come back and end up with some of the Phytase stability results that we followed up with since last year. So briefly, if you're in the room, if you have an NIR at your feed mill and you're measuring crude protein, fat, any other approximate analysis, a question we often get asked is, well, can I just analyze that sample, or does that sample really need to be ground before being put in the machine? So you can see here we have this sample of ground corn that's getting ready to be ran in the NIR. And two of our grad students, Nana and Caitlin, took the lead on this project to determine, well, how does that influence my crude protein analysis, especially if I grind my corn down to 400 microns, is that already ground fine enough for this analysis? And what we can see is if you don't grind your sample, your crude protein accuracy on that measurement is going to be much less than what the laboratory analysis tells you. And if you grind that sample, you get, although these are statistically different, not far off from our target values of 20% crude protein. So no matter what your particle size, if you're feeding MASH diets and you want to use the NIR, don't take a shortcut, grind your sample before analyzing it. Second, even more important, if you have pellet samples here, you can see the large decrease in our analyzed crude protein value if we don't grind those pellets. So if you take cool pellets, put them in the NIR, measure crude protein, your accuracy of that sample is going to be off compared to your laboratory analysis or if you grind those samples. So very simple things, but something to keep in mind when you're preparing your samples for NIR analysis. Make sure you're grinding those samples before you analyze them, and your results will come out better. So while we're talking about NIR, typically we think about using NIR for proteins, fats, moistures, things of that nature, but we're starting to hear more and more about can we measure amino acids, and even recently, can we measure available lysine? So this becomes important when we start thinking about soybean meal that's been heat processed, although not a major issue in the U.S. if you're buying other sources, and then on the distillers front. And so recent calibrations have been developed with lysine, and we're starting to see more on the reactive lysine. So reactive lysine in this sense with NIR is going to be what if you sent a sample to Missouri and had them measure available lysine. And so Kara Dunmeyer received some mechanically extracted soybean meal, and then she put it in the autoclave to create this what we called over-processed soybean meal due to the browning reaction to reduce that lysine. Sent samples that have reactive lysine measured and available lysine measured, and you can see there was a really nice correlation between the two to predict over-processing of soybean meal. And so this was really good initial data. We look forward to what the future holds, and where we really see a lot of opportunity, or at least what I see opportunity in, what I'm excited about, is how can I apply this to my receiving of distillers grains, trying to measure quality and lysine. And so typically when we look at the literature or think about the past, we hear lysine to crude protein ratio. If you have a lysine to crude protein ratio above 6%, you have a good quality product. If it's below, something you may want to consider. Some questions we have in our lab are lysine to crude protein ratio, that's a good measurement, but now if we have this opportunity to even get more information out of the sample, should we be considering reactive lysine to crude protein or even reactive lysine to total lysine and what does that tell us from an ingredient quality standpoint. So we look forward to what the future holds. Hopefully we can improve the precision, accuracy to get quick estimates on these nutrients and their availability and incorporate those into our feed mill strategies and nutrition strategies. So next off, this is a fairly simple question, but actually had big implications in our lab. And so this is a Holman PDI tester. So typically when you think about the K-State Feed Science Group, you think about the tumble box. And with that tumble box, you spin pellets for 10 minutes and then measure pellet quality. Well, now a lot of mills are moved to this NHP 100 Holman tester because you can analyze those samples in 60 seconds. So you put your pellets in the top here, and then it goes into a wind vortex that stresses those pellets, and it gives you an estimate of quality. Well, one simple thing that this test requires is for a filter to be put on top of that. And typically, a filter is something that is easy to run out of, and in my mind, I don't think it should make a big deal, so I should be able to complete the analysis anyways if I run out of my filters. Well, Dr. Stark proposed a question: if we run out of filters, can I go into my kitchen and steal some of Janet's brawny paper towels and use those? And we may have done it once or twice. And so what we did was just says, well, if you use the filters provided by the factory or the Tech Pro company, the brawny paper towels or none, how does that affect your PDI analysis or your pellet durability index? And you can see without the filter, you actually reduce your PDIs. So that dropped from above 90% down to 80%. So that your accuracy is going to be off in that pellet quality test. The more concerning thing is after seeing those results, we kind of laid this over to another pellet quality test. And what we found in this experiment, when we ran it without a filter, the PDIs dropped from 89 down to 56%. So if you're in a mill trying to produce good quality pellets and you have to report those numbers to somebody, your lab technician could really mess up your bonus that week. And then the other concerning part is look at the variation in these numbers compared to with the filter. So if you want to stress those pellets harder, what I would do, just increase the time you run that Holman tester, but use that filter because you're going to get a more consistent number. You're going to reduce your variation and improve your precision. So once again, something really minor that can make a big difference in the quality of your samples. So lastly, I'm going to follow up to where we left off last Swine Day, and we had this theory of phytase stability and how the pelleting process influences stability. And one of our students, he actually graduated or defended his thesis last week, Marut. I'm not even going to try to say his last name, but now Dr. Marut, he had this theory where he calculated dye retention time and thought that really made an influence on our stability results, and it all made sense. And so what Marut did was calculate how he can go into our feed mill, create different dye retention times, and then test how that influences phytase stability. And so by doing this, he used two different pellet mills, our 1-ton pellet mill and our 3-ton pellet mill. He put different dyes on, so one with an LD ratio of 6.6, a 10.6, and a 9.3, and then he adjusted the production rates. And by doing that, he had dye retention times across this scenario ranging from 1.6 seconds to 4.2 seconds. And so what Marut found is, so remember, this is our 1-ton pellet mill, LD of 6 at 1.6 versus 2.6. When you compare that dye retention time of 1.6 to 1.6 with an LD of 9.3, there was no difference in phytase stability. So dye retention time was the same, a thinner dye versus a thicker dye, same stabilities, okay? However, in this example, when dye retention time was the same, stability decreased from 73% down to 10%. Once again, everybody has a protocol till the pellet mill plugs, right? So what happened in this experiment is, so this top number here represents your conditioned mash samples. The bottom number is your hot pellet temperatures. So the difference in those two is the heat you're generating across the die. Really not a big difference in hot pellet temps compared to conditioned mash for these two treatments. But when we put this 10.6 dye on our 1-ton pellet mill, our hot pellet temps increased to 203. And so what we really can conclude from this is once you hit that temperature, you're going to denature the enzyme. So what's lacking in this experiment and would be great for us to rerun is there a difference in this 4.2 and 2.6 if we have a hot pellet temp of 186? Okay, so we don't have that answer yet, but we do know if you're going to measure phytase stability, we need to be taking hot pellet temperatures. And so to kind of confirm this, we went back to some of the data that Courtney Trulock had collected over the years. And you can see here, when you plot it on a temperature basis versus a stability basis, Courtney had taken conditioned mash samples in the gray dots and pellet samples in the purple dots. And when you match those up with their corresponding temperature, there's no difference between the two. And as you increase that temperature, you decrease the stability. So at this point, we're still lacking data in this area. If you have a lower conditioning temperature but a hot pellet temperature below 175, what's that going to do to stability? We need to revisit conditioning time and how that influences stability now that we know where some of our parameters need to be set. But the take-home story for me today is if I'm concerned with phytase stability, I need to be measuring the hottest temperature that my feed achieves. And the best answer right now is going to be hot pellet temperature. But we need to think about how we're conducting that. Are you using a styrofoam cup, a coffee mug, a bucket? Is there a way we can measure dye temperature? Is that going to be a better estimate? So these are some things we have to work on to figure out how can we actually measure this highest temperature that our feed's hitting in order to determine where we're going to be with our stability analysis. So take-home messages. Grind your samples before you use the NIR, put a filter on your Holman, and measure hot pellet temperature. Thank you.